well, my plan was to sort of try and address people's questions. I think I'll probably spend some time on Monday doing this as well. But let me start. This person didn't put a name on the slide, but that's you. Okay. Well, let's go for it. Let's start with your questions. So the first thing is definition. I think several people asked about gradient-like vector fields. So let's. Okay. So what are we doing? We're going with filling in gaps. Filling in gaps, or just reviewing things that I said too quickly. Okay. So what is a gradient-like vector field? Here's a Morse function. F x, right? A gradient vector field. V on x is gradient-like. All I really want to say two things. If the first thing is away from critical points, df of v is positive, negative if you prefer to go down. And so this is equivalent to saying, so I can, f is a function from x to r, right? If I wanted to do Circovite Morse theory, then I wouldn't have a little df of v, although there is sort of such a notion. But I could also say, equivalently, I could say capital df, right? Then that, df of v, all I really care about is df of v is not 0, and then pick a direction. The capital df of v is an element of the tangent space of the target manifold, which if it's R or the interval, this makes sense. If it's sorry. Okay, so that was clear what that means, right? And that just, actually, maybe I should say even more. Geometrically, V is transverse to level sets. And then the second thing is that near the critical point, coordinate systems, a coordinate system x1 and xn, with respect to which two things happen. The first thing is that f takes the standard models. F is the sum plus or minus x squared plus f of the point, I guess. Point. And the second thing is that v is equal to the vector in that coordinate system. I'll just say sum plus or minus 2xi. In other words, it's just the standard Euclidean gradient vector field in that particular model, right? Does that make sense? So this is the day of resolving unresolved things. So don't let me push it. So that's the definition. And now, a good question that I should know the answer to, but don't, is how important is this second condition? Okay, so this is telling you what is going to happen near the critical point. Now, what you could do, so what's typically somewhat sloppily done is just say, choose any metric, choose a Riemannian metric. Level G on X, and then let V equal grads of G of F. Which, if you remember, the way you think about a Riemannian metric is you think about it as giving a isomorphism from the tangent space to the cotangent space because it's an inner product. So it gives an isomorphism between a vector space and its dual. So then that isomorphism is typically called G tilde. G tilde inverse of df. Where G tilde is the map from Tx to T star x. And this will not, in general, give this condition unless the metric is particularly nice, right? So the interesting question that I don't really know the answer to is how bad can it be? How bad can how non-standard would the gradient, like if I take some metric with non-trivial curvature, say at a point, and then I have a normal, but that curvature somehow, the principal directions of principal curvature or whatever are totally unrelated to, let's say, the model for local critical. And how weird can the gradient vector for such a metric be? I don't know, but and maybe it's you really can just get everything just as well. But what we really want, this just is a convenience which we can achieve, and this and with this convenience we have, in particular, we know exactly what we're going to know exactly what the ascending and descending manifold look like. And that's really why we want this. And it's possible that with a little bit of analysis you could get all of that for a general metric. So the point is that that gives one problem. That's just automatic because, well, figure it out. Well, actually, maybe should we just do it? Let's just check why is df of v positive, right? So that's because df of v, well, saying that v is g tilde inverse of df means that if I wanted to df of something, I could just as well use v, but I use v using the metric g, right? So this is g of v, and since v is, but since df is non-zero, v, and going back by a linear map, v is non-zero, therefore, and this is an inner product, so that's positive. Okay, so that's where that follows from. And when v is equal to 0, when df equals 0, v's got to be 0. So, I mean, if anyone wants to figure out the answer to my question is, how far off are we from 2 if we just use arbitrary metrics? It doesn't matter. And I mean, I'm sure the answer is no, and I just never bothered to figure it out. I've just been happy to say that we can always construct this. So let me give you a proof now of, I actually sort of gave a proof early on, but I'll do it again for the existence of gradient-like vector fields. But the proof I gave was constructing a metric and patching things together. So let's forget that proof. Let's just give a different proof where we don't use a metric at all. So the proof of existence is just going to go chart by chart. So cover X by chart by coordinate charts. Now what I want to do is such that each critical point is in just one chart. And that chart is a Morse chart. by which I mean a chart in which the function has that nice number. All right, so on each chart, you can, so on each chart, chart V, any old way you want. You know, now this is just a question of R. You got an open set in Rn, a function on it with no critical. Well, when it's in the special neighborhoods of the critical points, you just construct it exactly that way. Just make it equal that, right? And then in the other charts, where there's no critical points, you have a function from Rn to R with no critical points, and you know, just take a gradient of the standard Euclidean metric is good enough, or any other way you want. You've got level sets, you just pick some big transfers. If you like, you could even make your chart small enough so that actually it's foliated by just parallel planes, right? And then you just take the last direction. Anyway, you construct V, and then the point is, then you attach them together with a function with partition of unity. And we want to know that we still satisfy all these conditions. Okay. And the point is, because each critical point is in just one chart, then at that point, we're never actually taking an average of any two vector fields or anything, right? So at that point, we're satisfied immediately, and then we just have to vary. So in other words, the overlaps of charts do not involve critical points. And then you just have to look at just this transversality condition, or this, anytime you have a positive condition, right? So, you know, df of a linear, df of convex combination of these is positive with df of each of these positive. And that's it. Okay? Any other questions anyone wants to ask about that? Like I said, the super helpful thing about this is that if you want to know the gradient, like, you know, if you want to look at ascending and descending manifolds, then once you get close enough to the critical point, any flow line when it gets close enough to the critical point is completely standard, so then you know exactly what's going to do. I think there's something else that was asked by someone else that's related to this. Well, okay, I don't know if anyone asked this question, but I might as well review it again. The point is, now suppose that I have so what I want to talk about a little bit is the relationship between varying V and isocopies of ascending and descending manifolds. So the easiest case to understand is if you have a critical point P, and then so case one is if V stays constant in the neighborhood of the critical point P. Okay. But then it does something else elsewhere, right? And then you want to look at, say, the descending manifold for P, right? And we want to look at consider so then let's say let y be some regular value less than f of P, and consider. So I'm thinking about a one parameter family, V sub T, but it's actually not going to be dependent. It's not going to change with T in a small neighborhood critical point. Okay. Then we consider the descending manifold for P intersecting with a level set below E. And I want to descending manifold, but there's sort of, this is indexed by t, because as v changes, v sub t is changing elsewhere, it's just not changing by p. Then I've got this descending manifold. The claim is that this is, let's suppose this is, for the moment, suppose there's, let's see, y equals f of p minus epsilon. So it's just below there, right? Anyway, the point is, suppose it doesn't run into any other critical points all the way down, right? Then we know that this is going to be diffeomorphic to a sphere of something, index I minus 1, where I is the index of the critical point p. And then the claim is that it's just a sphere moving around by an isotopy. So the claim is that this just moves an isotopy. Well, actually, there are two sort of, if you believe that for all t there's this descending manifold and it moves smoothly, I mean, that's just sort of obvious, right? But another way to think about it is, I mean, really, that's sort of all you have to say is that that you can actually maybe that what you would want to do is say you construct this, for each. What we really want to do is say that for each t, we have an embedding, we have a map from a ball into our manifold X, whose image is the descending manifold. And that map varies continuously with t, and the way you would construct that map is you'd start near the critical point.
This is for some like small values of t.
Yeah, I'm just going to let t. I'm assuming that I'm not running. What I really want to do is assume I'm not going to run into any other critical points. I'm not, so the handle slides are not coming.
So you're saying there's like some interval in t space for which this is true, is what you're saying?
Yeah, exactly. Well, what I'm really saying, maybe the best situation of what I really want to do here is assume that maybe I should specialize to the case where, let's be more precise about the case that we can get here. So, I just have some y less than f of p, and, well, the point is, t is not, the function f is not varying, okay, and no critical values in the interval from y. Okay, that's all I need. So the function is not varying, just the vector field. Okay? So there's nothing to run into, no other critical points to worry about, right? And so then I want to say that this is moving around by an isotopy. What do I mean? What I really mean is that I can actually explicitly construct a one-parameter family of diffeomorphisms going this way, right? A one-parameter family of smooth embeddings of the sphere into here. And then that's what an isotopy is a one-parameter family of smooth embeddings. So how would you do this? You could try to, you start at your point P inside your local coordinate chart. So here's sort of this chart. Inside that nice chart, this is your x1 and xi, right? And then I want to construct a map from a sphere, and then farther out here somewhere. Go, I'm out of the chart. This is x versus y. Right. So what I would do is say, let me tell our goals to construct t and embedding let's say phi sub t from the I minus 1 sphere into f inverse of y. Right? Using this flow. So what I would do is I'd actually take the I minus 1 set, take the I minus 1 sphere in, because the best thing is phi sub t. Let's be very precise. Okay, so phi sub t is going to be a composition of two things. Let's say c sub t composed with some alpha. And alpha is going to be embedding an si minus 1 into this as into the unit, radius epsilon si minus 1 in the x1 of xi in this coordinate term. Nice coordinate term. So first I'm going to embed the way over here I have standard si minus 1, standard 1 in Ri. I embed that here as a sphere of radius I minus 1, a sphere of radius epsilon, some small epsilon. It's just so it fits inside this coordinate chart, right? So it's on the descending manifold. It is the boundary of a descending disk of radius epsilon, because that's the descending disk of radius epsilon. Remember the gradient, the upward gradient vector field is coming in like that. And so then there's my sphere here, right? And then phi and then c sub t goes from maps from alpha of si minus 1 back into f inverse of y, and it's just flow down along v until you hit f inverse of y. If you like, along minus v. So if you like, what you could do is in the interval from this level down to here, you could rescale v so that it has the appropriate length 1 with respect to df, so that in a constant amount of time you hit this level, right? And then you flow down, and that gets you. Okay? And then everything depends. This depends smoothly. That one of the theorems about solutions to ordinary differential equations is that if you verify the parameters in your ordinary differential equation, the solution varies smoothly. That's what you're going to use variance. So that's why this moves by an isotope. Conversely, suppose we want to move it by an isotopy, and we want to construct a vector field that makes it move by an isotopy. I won't write anything down for this, but the point is then you just say, I've got a collar, I look at some section just above the level set where I want it to move around, and I've got a vector field which I parameterize that thing just above it as a product. Okay. Now I want this guy to move around, so I can think of, it used to, the sphere used to go straight down, where straight down was with respect to a fixed gradient-like vector field. Now I want it to go over here. So an isotopy is a particular path in f inverse of y of that embedding. I can sort of use that path to construct a cylinder that flows down, right? And so for each slice, I've moved a little bit more. And now that gives me a vector field, which is tangent to that cylinder, and then I extend that vector field to the other. So all I am doing is pushing the vector field over somehow, so it slides like this. So I can modify a vector field. An isotopy gives me a one-parameter family of vector fields. Maybe not uniquely, but it gives me one. Right? And so we know that it moves by an isotopy in a level set just below it where it hasn't run into any other critical points. And then the question is, what if I want to know what happens much farther down in some much lower level set where it might have run into critical points, right? And then you're just going to use that same fact. You say, so if I want to know how so here's P, and here's some other critical point Q, and I've got this in here, the level set f inverse of y, we know that the descending manifold just moves by an isotopy. And then I want to know what happens at some level set f inverse of z or something down below there. And the point is, well, it moves by an isotopy here, so the parts of it that don't run into Q move by an isotopy down here. But what about the parts? Well, then all you have to do is think about it. You think about the ascending manifold of Q. For example, if Q and P have the same index, then we expect the ascending manifolds to be disjoint, except for isolated times they might intersect, and we say, well, what happens if they intersect? And in isolated time it intersects. So you say, the point is, anything you want to know about what it does down here, you think about how it interacts with the ascending manifold up there. So for a Hempel slide, it'll cut these, you'll have two circles in this dimension, and then they'll come, and then at some isolated time, one circle will cut transversely across the other circle, and you can see that turns out you can sort of then you use local model for the handle to flow everything down and see what cutting across does down below, and that turns out down below that it does this swallowing. But there were some other questions about handle slides that I'll get to later, but I think that's all I wanted to say about it. So are there any questions about this? Okay, the other question you asked, sorry, Joel, was how why a trivialization of a normal bundle up to isotopy specifies an extension to a solid torus up to isotopy, and that's crucial to thinking about handles.
Wait, I'm sorry, what's the question?
I'll state it up here carefully. It was something we used when we reduced handle attaching data to framed spheres, right? The crucial observation, the crucial step was to say that you wrote it out so nice that I'll just copy it from here. So trivialization of a normal bundle. So I've got an SK minus 1 embedded into an n minus 1 manifold as the attaching sphere for a handle, a K handle, an eight-dimensional K handle. And the claim is that the trivialization of the normal bundle, this is phi, normal bundle of phi at SK minus 1 up to isotopy determines an extension in capital Phi from SK minus 1 across all of these of the n minus dimension n minus k into n up to isotopy. Okay, so in other words, by extension that means that this is SK minus 1 across 0, right? And first of all, just to be clear, this determines trivialization. That's the first thing, right? Because if in SK minus 1 cross Bn minus k, I already have a fixed trivialization of SK minus 1 cross 0 coming from the n minus k unit vectors in the Bn minus k direction. That gives you a trivialization of the normal bundle here, and you push it forward since that's an embedding, and that gives you a trivialization here. Okay, so what about the other direction? And the point is that what you would want to do is say, first of all, forget about the up to isotopy, right, here. Suppose I fix the trivialization here, so that gives me vectors everywhere, right? What I want to do is use that to, actually, no, here's the right way to say it, right? The right way to say it is using the exponential map. So you use the exponential map, and you take the exponential map will from the normal bundle.
So you've again picked a metric.
What's that?
You're fixing some metric.
Correct. To get an exponential map, I have to fix some metric. Right. So I'll just fix a metric. I choose a random metric. It doesn't have to have anything to do with vector field stuff, right? Choose a random metric to use to get an exponential map, and then that gives me a map from the normal bundle to M. Okay, well technically the exponential map is a map from the tangent bundle of the manifold to the manifold, but I can restrict it to all kinds of different pieces, right? And in particular, the exponential map. Remember, what is it? You start at a point. If you have a vector in the tangent space, then you want to figure out where that vector should go in the manifold. So you start at that vector in the tangent space is always based on a point. You start at that point, and then you've got a Riemannian metric which gives you a geodesic in the direction of that vector. And then you flow along that geodesic for distance given by the length of that vector. And that gives you a point in the manifold. And the key thing about it is you can, so I'm going to restrict to the normal bundle of this subset. So that means I'm at any point on this sphere, I'm only going to be interested in flowing normal to that sphere, right? And so then, so that's going to, and the key thing is that for some open neighborhood, for some tubular neighborhood of the zero section of this thing, I'll get an embedding. Okay. So this gives, so EXP restricted to some open neighborhood of the zero section is an embedding. Now, but if we've trivialized this normal bundle, we can just think, then we've identified this. This has been trivialization, means this normal bundle, we've identified it with we identified with sk minus 1 cross Rn minus k. Right. So an open neighborhood of the zero section is, so this section, open neighborhood of the zero section is going to be, it's going to be, even its identification is sk minus 1 cross some n minus k ball of some possibly small radius f1. Right. And so that's this extension. Now, if we vary that, so then what you have to believe is, okay, you start wiggling around this, you start varying this trivialization, right? Which means you're varying this diffeomorphism, right? In a one parameter family, right? So, but you're always, it's always, all you're really doing is changing the, when you vary this it's a trivialization, so you're always it's always still, the sk minus 1 part is not moving, it's the fiber part that's moving, right? And so really what's going on is you're getting a one parameter family of maps from sk minus 1 into gl n minus k. Okay? So an isotopy of the trivialization is going to, for each time and for each point in sk minus 1, I will change my my fiber by some linear map. And for time 0, it's the identity map. So this gives a sort of delta sub t from sk minus 1 into gl minus k, right? And with delta sub 0 equal to the identity. But anyway, the point is, such a thing, then you can, if you pre-compose, oh, what I lost track of it yet. We got this embedding, right? Right. So now this embedding goes in here. If I pre-compose that embedding with this isotopy, right? Then I will get a one parameter family of embeddings. So that's how wearing this by an isotopy gives an isotopy here. And then I guess that's all to say. I guess the other point is, what about the choice of the metric? Right? So even if I don't vary this by an isotopy, I choose a different metric, I'll get a different exponential map. So then what you want to know is, as you vary the metric smoothly, any two metrics are connected by one parameter family of metrics. If you vary the metric smoothly, the exponential map changes smoothly as well. So that's, again, that's really, well, actually the exponential map is a second order differential equation. Is a solution of second order differential equation, but anyway, it's an ordinary differential equation still. It's not a partial differential equation. So you don't have to worry, but you still have smoothness of solutions depending on parameters and so on. I hope I said that. I don't think I said anything wrong. Okay, what else was something asked? Jacob, that's you. You asked about handle slides, frame links, frames knots, links. We did some examples earlier on handle slides. Did that help a little bit, or you want to do something more?
I don't really see what's happening when something's sliding over something else.
Right. Okay. So with framed knots, okay. First of all, you said you were, confused about what they are and how to work with framed knots or links.
That's kind of been,
that's been a little bit taken care of. Okay. So let's okay. So let's go back to the very beginning with handle slides. I mean, let's not take the approach of getting a handle slide from a one parameter family. Let's just try and do a handle slide, right? So the first question is, what handles can you slide over what other handles? And the basic thing is two handles of the same index. So I'm going to say I'm on an n manifold. Right? And then I have handles of the same index I, the only condition on I is that 0 should be less than I should be less than there. So you can't have to slide a 0 handle over another 0 handle because it doesn't have anything going down, right? And you can't slide an n handle over another n handle because they don't have anything going up. There's nothing above. If there's nothing below or above, then you can't slide one over the other. Also, though, you have to. I might be in a situation where the descending manifold for these two handles, the attaching manifold handles actually land in disjoint components of something, and then I can't. There needs to be an arc to connecting, and so you need an arc connecting the images. They're attaching images attaching spheres. Otherwise, it doesn't make sense to slide. So then let's do the very simple first example. Let's take a so here's a 0 handle. I'm going to build a 2 manifold, and then there's a 1 handle, and then I'll take another 1 handle and attach it. So what it means to slide this over that is to take its attachment. Well, if we wanted to, let's just do the simple picture first. Literally, we take one foot, the other foot's going to stay still, this foot's going to go up and over. Okay? So you get this picture over the intermediate stage where it attaches like that. And that's sort of a legal handle attachment, but we don't like to draw it that way because that's somehow non-generic. And you can slide down one way. This is the point at which the ascending manifold for one of the makes one critical points, and the descending manifold for the other coincide, and then you slide it and continue down. Very sloppy picture, but you know it, right? Okay. So that one handle slides are pretty easy to visualize. The two handle slides are the hard ones, and beyond that, I'm not going to even talk about it. So, first of all, if for a 2 manifold, it doesn't make sense to talk about 2 handle slides because of this thing. You've got to be between the minimum and the maximum dimension. So we'll do 2 handle slides for h = 3. I think the best example I can give is the following. I'll try to actually draw kind of a nice picture here. So I'm going to imagine I've got a 3 manifold that I've already constructed down here, and then here's the top of my 3-dimensional cobordism, and let's say I've got a particular. I'll try and draw a 2 handle attached like this. comfortable with that picture as that being a two-handle. This is a two-handle because it's a B2 cross B1, right? And it's attached along the boundary of the B2 part cross B1. That's one cross B1. That's good. So in this case, if you just attach it here, for example, a two-handle separates the boundary, right? After you attach it, you used to have this thing, now you've got a new two-sphere component in there for the boundary. Now let's suppose we slide it over another two-handle, which happens to cancel the one handle. So suppose over here I have a so suppose that's my one handle, but then I also have a two handle. Like this. Okay, does that picture make sense? So I've got this one handle and then just this thickened membrane stuck in there. And now I want to slide this two handle over that two handle along an arc there. Well, so okay, first thing I said, I've described sliding as find this pair of pants, where I've got the three boundary components, right? But in practice, what you do, you'll see the pair of pants after we do it. In practice, you usually find an arc from one to the other, and you just push this thing along. So you want to visualize just taking this thing and pushing it, and then it's just going to, a little bit of its attaching map is going to slide up and over until it's no longer, so for a little, there's going to be some intermediate phase, which I hesitate to draw, where it's sort of going to have a finger that goes up and over like that. And it's going to go over a little bit onto the surface of that other two handle, right? But then eventually you get it so it goes off. Right? And then once you've done that, you discover that what you can then, I stuck the picture around. So you just have this single one handle and canceled by two different two handles simultaneously in some sense, right? You have the single one handle in the middle, and you have one, then you sort of have one two handle right there. And then you have another two handle that comes over here, goes up and over. That's its attaching map. So then you just get worse and worse, but you see what's going on, right? And of course, remember the critical thing to remember is that at some time, so the descending manifold for this, here's the critical point here, here's a critical point there. And there's two critical points. The descending manifold for this comes along is this disk that whose boundary is the circle. The ascending manifold for this critical point is 2 points, one on either side of that thickened up disk, because that's the boundary of the one direction. And so there's one moment when it hits there, and that's sort of the moment of the handle slide. And then, it's true that when we sort of, you could say as soon as you've gone past that, you're fine, you're generic again. Except that we want to push it all, we sort of have this vision, of, anyway, we want to get all the way past the two handles in some sense. But that's just an artifact of the handle decomposition rather than the Morse function. And incidentally, after that, you could then take this vertical two handle and slide it sort of over, but it's really sort of looks like sliding under, right? And get it off. And it'll be down here, and then just this one handle will be canceled by the other two handle. And then you could actually cancel them. And if you draw a surf graphic for that, what happens is you have a two handle for a little while, and then you have a birth of a canceling pair of two critical points. Because I was imagining first there's this two handle, and then this canceling 1-2 pair appears, right? So in time this happens. And now what happens? I'll draw a vertical dotted line, which means that this two handle that was there to begin with slides over the other two handle. Now, if you think, now I want to slide this over that. Now, from a Morse theory point of view, from a handle decomposition, there's no such thing as above or below. But from a Morse theory point of view, for this handle sliding to happen, this critical point's got to rise above that one. So it's got to be a crossing. And then you can have a slide there, where this sort of slides off, and now these two can cancel. So that's the swallowtail animation. Okay. Right, and then the question is, how does the surf graphic give you information about this? And so, well, this is sort of an example, but if you just, the surf graphic itself does not give you information. If the surf graphic is, well, it depends on what you mean by the surf graphic. The surf graphic as just the image, sort of the graph as t varies of the critical values. That's what I think of the surf. That doesn't tell you the handle slides. The handle slides are the times at which you have a flow line from index I to index I, right? And pointing like that. At those times, you have some. Now, frequently, sometimes when people say surf graphic, they mean sort of the graph of the critical values as over time, together with vertical dotted lines whenever handle slides happen, right? And then that tells you when. It still doesn't tell you exactly. It doesn't have all the information. Just like saying there's these critical values doesn't tell you much about the Morse function, right? But it has some information. However, there's one case that I think is worth thinking about, which is that suppose in the surf graphic you see two critical values of the same index cross like that, right? So let's say this is index 1 and this is index 1. Right? You can even think about it in this case. You could ask, can this one parameter family of Morse functions be modified so that those two crosses don't happen? And I can't remember. I think I asked about that, talked about this briefly before. Can we do this? And so the answer is no if there's a handle slide in there. Okay. And the reason is that if I got two handles like this and this one slides over this and then that slides over that, well, no, if this is below this and then it goes up, slides over and then goes back down, then it's flipped. It's somewhere different, right? And so the sort of handle attachment over here is genuinely different than the handle attachment here. And so, but if you have a one parameter family like this, you're never going to achieve it because this guy needs to get up in order to slide. So somehow, the only thing I can say for what the surf graphic gives you is if you have sort of crossings like that, which can't be eliminated in some sense, whatever. If you know for some reason it can't be eliminated, that means there's got to be handles. Okay, I'm going to see if I can address Matt's question in just a few minutes. So, okay, he said he'd enjoy hearing more about gradient vector fields and flows associated to them. Okay, in particular, he wants to think about Morse, Heegard splitting on a 3-manifold and the gradient vector field. I'm going to draw it schematically first. So you've got some 3-manifold. You've got index 0 and 3, and you've got your index 2 critical points and your index 1 critical points. And you've got your Heegard splitting like this. And then you've got a flow. Now, all right, so now the flow, let's say, the vector field initially just goes up. And Matt's proposal is to modify it to take a negative on 1/2. And then you want to use some kind of bump function, right? So I think you want to think about a flow.
Well, like
you want to use a flow that everything flows down towards the middle, right? So this is a perfectly reasonable thing to construct. You take a given gradient like vector field, you take minus it up here and the original thing down here, and then you interpolate using a bump function in the collar neighborhood, so it goes to 0 there. Okay. So this is the flow that flows from out into the middle. And then, so then in particular, it wants things, say you take some submanifold here, and you just flow forward, flow towards the middle. Will it get there, or will it hang up on these things? And the answer is just a dimension count there. So the way to think about will this submanifold get hung up on these critical points or reach here? Does everyone understand the question? You just take this submanifold and flow it and see, does it get all the way here? So all you have to do is look at the descending manifold for these critical points. Of course, your manifold may even wander all around both sides, right? But at the moment, consider this. You take the descending manifolds for these guys. If you have the more general case, you take ascending manifolds for those guys as well, right? And as long as they're disjoint from this manifold, submanifold, you'll flow all the way to the middle. Because the only points that don't get here, well, of course, there's the critical points themselves, never go anywhere. And then there are points there, the descending manifolds for these, those are the points that get sucked into here, and the ascending manifolds for those are the points that get sucked into there. Okay, does that make sense? And so now this is dimension 3, index 1, and index 2. These are actually just one-dimensional. And so are these. So if you've got something that by dimension counting can be isotoped to be disjoint from something one-dimensional, then you're good. It will flow. So in particular, your question was, what about a knot? So a knot can flow all the way in here, but a surface might not. So an embedded surface in the 3-manifold might get hung up on these critical points, but a knot would not. However, the one thing to remember is, well, okay, if you use the flow, you've made it 0 here. So you never actually get there, right? If you try to force yourself to get, so you can get into a neighborhood here, and that's an ambient isotopic manifold actually. And you get into a neighborhood, you get you're not in here. Now you can say, let me just smash it down, even though the flow doesn't do it. And then you may have crossings, of course, because once you get into the neighborhood, you've got your knot lying in a across the surface. You project onto the surface, and there's no reason to expect not to create singularities of a knot.
So I guess.
But any knot can be projected onto the Hagar surface this way, and it'll be some thing with crossings.
So I guess you don't have to worry at all about it linking with.
Well, if it links,
ascending and descending manifolds.
It links, but it doesn't intersect. That's all. So it's hard. It's a little.
Yeah.
So we need. All right, I understand what you're saying. The we should do a quick example. People need to leave. We're out of time. You can go. I won't be offended. But let's just do the case of the bottom half just has a single index 0, index 1 critical point. So it's a torus, right? So there's the index 0. Here's the index 1 critical point. Here's the descending manifold for the index 1 critical point. Right? Now suppose I have something that links it. Right? And now I flow to the Hagar surface. The Hagar surface is the boundary historically just flowing away from this descending stuff, and we get out to here. No problem. So the linking, you're thinking that you're trying to push it past or something, but you're not actually. You're flowing just away from it. That's fine. More generally, you just got this genus 3 antibody. You're just flowing away from wherever you're. And this bouquet of circles inside there. And if you link it, who knows how you might link it? It doesn't matter. You're still going to have some well-defined way to flow out to the boundary. Processes. You might develop a crossing which will flow out to the boundary, but that's fine. All right. I'll do more questions on Monday.